Welcome everyone. This is the 8th part of my coil binder building series. So I have another big progress or considerable progress. So I would like to share the details with you, and I would like to show you some new stuff that I have implemented in this stuff. So you could see it on my earlier videos that I'm more or less done with the structural part here. So I have a custom feeder, I have the structure, and I found some nice holder for the, let's say, source of the wire. And then I'm also more or less done with the electronics part. I have a first iteration of the PCB, and I figured out that there are some mistakes that I have done, especially with the pin out for the display, which I will explain you later. So there is a version 1.1 PCB which works perfectly, and at least based on my inspection doesn't have any issues. So now the whole system works, and I can create more or less reasonably looking coils, but of course, as always, things can be improved or things can be made in a better, more efficient way. So those will be for the next parts. But in this video, what I'm trying to tell is I quickly tell you what are the things that I considered when I built the mechanics, what are the things that I considered when I built the electronics, and I finally quickly show you how the code looks like, and I give you access to everything. So I will share the 3D parts with you, and I will provide a link where you can buy the PCB directly, and I will give you a free access to my source code, which you can modify up to your wishes or your ideas. So first of all, let's start with the PCB, and this is how they look like. And why I say they, because there are two of them. This is the version 1.0 and this is the version 1.1, and this PCB, both of them are produced by the sponsor of this video, PCB. So PCB is a service provider specialized on PCB making and assembling, but they also have services such as 3D printing and CNC machining. So ordering a PCB from them is a really simple task. You just go to PCB instant quote, and then on this page you just click quick order PCB. So you can upload your Gerber file, and then you fill up the rest of the details to customize your board and press save to cart, and then you can order it. And if you are already experienced in PCB design and PCB making, I really recommend you to check out their 4th PCB design contest. They have two main topics, IoT and robotics, and you can also choose your own topic if you will. And as you can see, they have really nice prizes, so it's worth to participate in their contest. So what you see here is that it's a nice 2-layer PCB. So this is the ground plane, and this is the parts plane. So we have a place for everything: the 2 motor drivers, the stepper motor drivers, the connectors, the microcontroller, 3.3 volt regulator, and then there is a part for the display, the buttons, and the rotary encoder with a pre-manufactured board, which looks like this. So you can just plug it in. And the mistake I did here is here. So with the 1.0 version, I flipped the order. So instead of going from here towards this direction with the perfect pin layout for this kind of Nokia display, I accidentally flipped the pins. So as this would be the normal, let's say, direction, now this is the direction how the pins are laid out on the PCB. So you can put on the display upside down and you will have the perfect proper connections, but then my code will not work. So either you modify the code, which I did not want, or you make a new PCB. So I made a new PCB, And the things I did is I basically moved these connectors a bit more towards the inside. So when you put this board in an enclosure, the terminals, these guys, and those which like accept these guys here, they don't stick out that much. So that's what I did. I made a bit thicker tracks for the ground here, which is not really necessary in my opinion, because the ground anyway goes on the ground plane, but whatever. More thick parts towards the 3.3 regulator, as you can see, much thicker. And then I rearranged the wires a little bit for the rotary encoder. It looks a bit more aesthetic with these kind of breaks in the track than here. And then, as you can see, with the order of the old pinout, I could get down the 3.3 volt here to the switches, but here I cannot really do that because I have to go, as you can see, in quite tight routes, or I have to go through quite tight routes to reach the pins, so I don't have any space left for like ideally place the 3.3 volt. And actually that doesn't look really professional to just bring it here at a large empty spot. So what I did, I have the 3.3 volt here from the PCB, from the microcontroller. So I just bring it down this way and then bring it to the two buttons and to the rotary encoder. So basically that's what I did. But otherwise everything is unchanged. So I just maybe cleaned up the connections here and there, but nothing really changed in between the two iterations. But now it seems that this version 1.1 works properly. So that's regarding the circuit board. So this is the old circuit board, and you can see how the parts are placed. So we have the terminals for the two motors and for the input power, which will power the two stepper motor drivers, and we'll have some connections towards the 3.3 voltage regulator, which will power the microcontroller, the buttons, and the rotary encoder, and finally also the LCD. And then this is the new board. It's basically the same parts, but now it works as it intended to work. So I did not have to do any kind of crazy jobs as I did it here. And probably you can see some wires here because I had to do some very ugly soldering. But now I have this, and it works very nicely. So in the coding part I will show you how to upload the code, because this is a different microcontroller, an STM32F401 type instead of, for example, a blue pill or something like that. And I'm not using the USB to upload the code, but I'm using the ST-Link, which uses these 4 pins at the end of the microcontroller, these 4 guys here, and it's very easy and fast. But I will show you how to set up the Arduino IDE, first of all, to be able to upload code for this microcontroller, and also how to upload the code basically. And you might ask why I picked this kind of microcontroller. The reason is very simple. It's much more powerful than the STM32F103 blue pill, and it's cheaper and it's more available, because nowadays we have this problem with chip shortage, and the blue pill is not really available, and it's like 3 to 5 times more expensive than this board here. So of course we want to make this as cheap as possible, at least within a reasonable range of quality. So that's about the circuit. And regarding the mechanics, so I have this thing at this end, as you can see. It holds the coil, but I bought several of these because I want to have some backup parts and stuff like that. But here you can see that a few parts is missing from here, which can be found here. And those few parts are these cones. And why I use these cones is because I can actually put the cones on this thing, on this shaft, if I could remove the shaft. So then, if I put the cone, that allows me to attach any kind of diameter of bobbin. So this is a tiny bobbin and it doesn't really need a cone, but I have this huge guy, and as you can see, yeah, it has a bit of a play, but thankfully I have this cone and now it's perfectly centered. So it's a really good idea to buy a few of these guys here, this spool holder or bobbin holder, because you can use the cones and then you can attach any kind of diameter, internal diameter of a bobbin to your shaft, as you will see it, if I'm not too clumsy. So now I attached the bobbin perfectly by the help or with the help of these two cones, and it's centered perfectly, and there is no play, there is no nothing. So the cones hold the bobbin perfectly in the center, and of course I can just attach it. Of course I have to take care of this nozzle, but it works very nicely. So I suggest you to buy several of these if you want to build an identical stuff and want to use any random internal diameter, because you can see that the whole diameter of this was almost as big as the wall bobbin here. So this is regarding the mechanical parts, and as you can see, I have this pre-made linear actuator, and that has this plastic, 3D printed plastic thing on the top of it, which is basically this part here. This is the wire feeder and the tensioner. So this is how the wire runs through here, and it comes out through a nozzle, which is an EDM wire nozzle. It has a ceramic coating inside, so it will not really remove the enamel layer from the surface of this copper wire, which is really nice because we don't want to short out our coils. So then before finalizing everything, I put in this coil just to show that something moves here, and then I show you the functionalities very quickly. So I just want to show that this thing actually works and it's useful now. So I powered on the board, and as you can see, there is a message here. It's just a welcome message, and the LED here, hopefully it's visible, it's blinking, and I just set the program up in a way that it indicates that the main loop is running by blinking this LED in every second. So we have several menu items, and the first one is the speed, which is expressed in steps per second. Since the microstepping is the same, 1600, this also means that the main shaft will do 1 turn per second if I leave the speed at this value. Acceleration is 800 steps per second squared. And then the number of turns is 130, that's just the default value. The wire diameter is, for this wire, is 0.35 millimeters, but you should always measure this. And here I did one improvement, is that when you modify the wire diameter, you actually start at the third digit, so the thousandth of a millimeter, because actually I figured out that it matters. So I want to change the third digit here with the rotary encoder, and if you rotate the rotary encoder, then that value will be changed by 0.001, as you can see. But if you push the button, then you increase or decrease the value depending on which button you press by 0.1, so you can see. And I made the code more or less foolproof, so you cannot go to negative value with the button, which is like just a safety feature. Pitch, this is for a future video, and then the width of the bobbin is basically this distance. Then the bobbin diameter, that will help us to calculate the consumed wire. Main shaft, if I want to manually move the main shaft, I just show you quickly that if I keep the buttons pressed, it will rotate the main shaft. And then the same happens with the feeder shaft, so I can move back and forth and set up the starting point for the wire. Then this is one of the most important features which I implemented based on a viewer's advice or request, which is the auto winding. So there are two options in the winding. One is that you just start the winding and you just build up the layers and you finish up when you completed the amount of steps which was required, let's say 130 layers. Otherwise, you can do another thing, is that you just finish one layer and then the motor stops and everything stops and waits for a user input. So in this case, you will have to press a button. So for example, you can put in a tape to cover the wires or do anything, but as long as you haven't pressed a button, the feeder and the main shaft will wait at the end of a layer. So if that is off, then that will happen, and I want to demonstrate that to you because the other function was demonstrated a million times. So then this is the menu where we should start the winding. So I just enter the menu. We see the arrow indicating that we are in, and I just press the start button, and then the shaft should rotate and the feeder should come to the other end of the layer if everything goes correctly. So now everything stopped. So we stopped at the end of the layer, and then this display says that it is paused and we should press the up button to continue. So now I just show you one example. I just press the up button and then the feeder will go that way and finish with the second layer, and it will stop again. So let's see what happens. So the second layer is done. As you can see, the feeder returned to the initial position and everything is stopped now. The display says that we should press the button again. And I don't press the button because I just don't want to finish with this procedure. So this is where we stop basically now. And as you can see, so far it seems to work properly. So I hope that this will work for you if you try to rebuild this system. So you could see that the circuit works, the winding works, the mechanism moves as we want it to move. So we only have one thing left. I will show you how to set up the Arduino IDE with this specific microcontroller, and then I will show you the most important parts of the source code. But of course I just upload the source code as it is, and you can dive into it and dig into it and see how it works. So let's go to my computer and check the rest of the things. So now let's see how to set up the Arduino IDE to be able to work with this kind of board. Of course you can find a lot of tutorials on the internet, but I just want to explain it here very quickly. So you go to File and then you open the Preferences, and once you open the Preferences you have this window in front of you, and you have to click on this Windows icon at the line of the additional boards manager URLs. And then if you visit my website through the link in the description, you will have this list of links, and you will need the first and the third one to have a full set of boards added to your Arduino IDE. So you just copy paste those links from my website. So now we have the links. So now we have to go to the boards manager. So we go to Tools and Board, and as you can see I already have items on this list, but if you don't do this, what I'm going to show you, you don't have these things. So I go to Boards Manager, I wait a little bit to load everything, and I type in STM32, and we have this STM32F4XX boards, and I already have it installed, as you can see, because it's grayed out. So you have to just press install, and also you have to install this part, STM32 MCU based boards. So then you can see on this list that this has the generic STM32F4 series. So you install it, and just to be sure, you can also restart the IDE. So once this is finished, you go back to tools, and now in the board you have several options here. But all I do is I will just show this STM32 boards group, and then you will see that I already have this selected, generic STM32 F4 series. So I select that, and then I go back to tools, and then board part number is the black pill F401CC. So I select that, and then as the programmer, which is the upload method, I just select STM32 Cube Programmer SWD. And here comes the last part that we have to do, and that is the following. So you go back again to my website and check the link, and that link will lead you to this website. And at the bottom of this website you have different links to get this software, which is an STM32 Cube Programmer. And with this you will be able to use the ST-Link and program your microcontroller using the ST-Link. But you need this software. So now everything is set up, so we can talk about the program finally. So I already have a video where I explained the code, but that's a different version than this. That's an earlier version. So I will talk about the more important parts in more details, and those parts which are changed as compared to the previous versions. But let's just see what this code has. So I redefined a few pins here for the Nokia display, but the original pins which are responsible for the SPI are the same, but the reset and DC pins are different, but they are basically locked because of the PCB that we are going to use here. And then also a thing that I changed is this kind of mode as I add this instance of the LCD, because previously I did not include all the pins in the argument, but with this kind of microcontroller I have to, otherwise it will not work. And then these are the two font files, and you have to make sure that these header files are in the same folder where you store the Arduino code. So then we use the Excel stepper library, and we have two stepper motors. So we have the feeder and the main shaft stepper, and these are pretty much locked again because the PCB determined these pins already. And then some pins which are also determined because of the PCB. So we have 3 pins for the rotary encoder and 2 pins for the up and down button. And we know now, I explained this million times in previous videos, how the rotary encoder works. So these are the variables which are needed for this. And we have a few timers, 2 for the rotary encoder, 1 for the rotary encoder itself and 1 for the button of it. And then we have another timer for the buttons. Then we have a bunch of variables, and since it's very well documented and the variables have quite self-explanatory names, I'm not going to explain them. But what they do is they just store the most relevant values, or they store our position in the menu, and so on and so on. And then these 2 variables are very important. They are responsible for the microstepping, and since the speed and everything depends on them, you have to make sure that you don't miss these values. You have to write the same number here that you set up by changing the jumper configuration on the PCB. Again, a bunch of variables which are self-explanatory. This just helps us to navigate in the menu, so the microcontroller knows whether we are in a menu or not. These 2 guys are responsible for the buffers to store the string which is finally printed on the LCD. And the direction multiplier is responsible for the direction of the feeder, whether it goes left to right or right to left. And then this is just a timer for updating the display, and these two guys are responsible for blinking the LED when we are in the main loop. And I wrote this line here, so whenever we upload this code by using the ST link and using the Arduino IDE, we have to do the following thing before proceeding with pressing the upload button. So you have to press the boot button on the microcontroller, keep it pressed, and then you just click reset. So you press and release the reset button, and after this you release the boot button, and now you can click upload inside this software. So then let's see what happens in the setup. So of course, rotary encoder, all pins are inputs. Of course, buttons are also inputs, and the onboard LED, the blue LED, is an output. We want to turn it on and off, so we have to define this as an output. We read the status of the two pins on the rotary encoder. So then when we start to rotate it, we will know the direction. And then, since an interrupt base thing, the detection of the rotary encoder, we have this kind of setup to read this pin as an interrupt pin, run this function when the rotary encoder is rotated, and look for a change on the rotary encoder. So it doesn't matter if it's a rising edge or a falling edge of a square wave, for example, both of them will be registered. So then just a typical setup for the two stepper motors, speed and acceleration, based on the values which we set up in the very beginning. And then this is a tricky part. I struggled with this a little bit, but I figured it out. So we initialize the LCD, and then we wait a little bit, we clean the screen, and then we wait again. And here you have to be careful. Sometimes this contrast is not the same for the same looking device. So always check if your display is not showing anything, change the contrast and play around. But play around this value. So maybe you change it to 50, or you change it to 64 or something like that. And then the bias, for some reason I also had to change this. 4 works for me. And I turned on the display mode as this. PCD 8544 display normal, and then I wait 300 milliseconds again, and I set up the font as the normal font, and finally I print the welcome message. And I commented this, so it's in a comment now, but sometimes I want to send or receive something through the serial, especially in the debugging and developing phase. I did this a lot of times. So it's good to have it, but you don't really need it when you have the microcontroller as a standalone stuff. So I disabled it. And then this is nothing else, it just blinks the LED very quickly when everything is finished here. So this is just indicating that the code is working, so far at least. So you can remove this highlighted part. And then loop. So what does the loop do? First of all, every 1 second, without blocking, it blinks the LED on the STM32 microcontroller. So what it does, it writes the blink status value on the PC13 pin. And then we changed the blink status to the opposite. So if it was 0, it becomes 1. And then we reset the timer. And then whenever we finished with everything and also 1 second elapsed, we come here and write the new status, and then the 1 becomes 0, and so on and so on. So it turns it on for 1 second, and then it turns it off for 1 second, and this is how it works. And also we look at different kind of flags, and we see if we have to update the menu position, or we have to update the selection if we enter the menu, for example, or we have to update the value if we change the value, for example. We are polling the buttons. It's perfectly fine because we don't really need that let's say time critical operation on the buttons. So it's enough to do that by polling them, and then we check the steps. So based on this, we will treat the motors and so on. And if anything of these are, and then finally we move the stepper motors. So since the main loop, basically this big thing here, runs very quickly, it's fast enough to poll these two functions in this kind of way. And you see that it is using the run speed to position function of the axle stepper library. So we are not using accelerations here, and it's not necessary because we are not running at high speeds. And then here comes a big part. So we check if the winding is running, and if it's running and 1 second elapsed since the last time we entered this part, then we count or calculate the number of turns done. And that is basically calculated in two different ways, because we have two different ways in, let's say, determining the amount of steps to be done. And these two ways are determined by the auto winding enabled variables. So if the auto winding goes as a true variable, we enter this part, and then we know that the main shaft total steps is basically the total steps which is needed to turn the main shaft, let's say 30 times. And what we do here is we check what is the main shaft total steps. We subtract the current position, basically left. So if we have still, let's say, 5,000 steps from the total amount of steps, then we have that number here. And this kind of difference is divided by the microstepping. So we know that the microstepping also determines the number of steps to turn the main shaft by 1 turn. And then this will give us the number of turns done. And here is just an example. But if the auto winding is not enabled, that means that the feeder and the main shaft stops at the end of each layer. We have to calculate this a little bit differently. And yeah, basically this is the formula, and I wrote a slight explanation and a small comment here, so you will see it, how it works. And after we recalculated the number of turns done, we update the display, and now we restart the timer with this line, and we have to wait another 1 minute to other 1 second, sorry, to enter basically this part and one of these branches of the if-else. So this was the main loop, basically. So this goes over and over. We see if we have to update the display, and we update it based on the rotary encoder and the buttons, how we interact with them, and also we step the stepper motor if it's necessary, and also we recalculate the number of turns done if the winding is running, and if we need to update it in time. So here I don't explain this part because it's explained in an earlier video, so please check that part. But what is happening for each of these menu items, that we are inside one of the menu items, we check the rotary encoder, and then we determine what was the direction of the rotary encoder's rotation, and based on that either we increase the value of a selected variable or we decrease it, and then we let the code know that we changed the value. So that will allow us to run the update value function, because this became true now. So we run this function, we update the display's content, and we change this back to false. So we are waiting for a new change. So we can close this function. So print LCD, this is just the regular welcome screen. And then let's see what happens when we check the rotary button. So this this is a polling function, so it runs in the main loop. So we read the value of the rotary button, and then we see that if it's 0, I wired it like this, and you cannot change this if you are using my PCB. So if it's 0, then we see if the elapsed time is more than 1 second. So you cannot have 2 clicks within 1 second. So this is sort of a debouncing or filtering of the bad signals. And what it does is that when you press the button and this was fulfilled, then we run into this switch statement, and based on the menu counter we invert the value of the selected item. So for example, the number of turns selected becomes from false to true. And then we have this update value selection. So this will allow a function to enter from the loop. And again, we update the selection and we just reset the timer. So after 1 second, another click can come, and for example, we can exit the menu. So this is how it works with the rotary encoder's button. So then we have this update menu position, and what this does is that when you rotate the rotary encoder, you change the value of this this variable if you are in the main menu, and based on the menu position we just print different things on the display, and that's all. And I just want to share one trick here, is that we are operating floats or operating with floats here, especially when we have the wire diameter, for example, or things like that. So what we have here is that actually the embedded float is not really nicely handled. So you cannot, for example, print it directly on the display. So what we have to do here is that we use this D2strf, and what it does is we have, let's say, the number of turns, and maybe this is not a good example, so I jump just to here. So we have this D2strf function. So this function has 4 parameters. First one is the wire diameter. In this case, this is the floating point number that we will convert into a string. And then the number 5 there is the minimum field width. And this is useful when we have, let's say, a string which has, let's say, 8 characters, but our number is just made up of 4 characters. Then in this case, the other 2 characters will be just spaces. The number 3 there is the number of digits after the decimal. So in my case, for example, it will be 0.321. So those 321 is the 3 digits. And the str-temp is the temporarily used string which stores the converted float. And then the str-temp can be now printed with this snprintf function. So this snprintf puts this str-temp into a buffer, and then this buffer, which is an array of characters, is printed to the display or on the display by this line. So it's a bit complicated, but first we convert the float into string, then we put the string into the array of characters, the buff, and then the array of characters is finally printed on the display. And then this goes on and on with different kind of things. So you can figure this out how it works. Then we have the update value, and this is the same. It does the same basically, so I'm not going to explain this, but this is when you update the value. So for example, you rotate the rotary encoder and you increase or decrease the number of or the value of the number, and then this function runs, because the menu position is just when you are navigating in the main menu. So I close this. It's the same principles. So selection, again, it's very simple. So whenever we press the button, this function is called when we are in the main menu. And what it does is that if we are, for example, at this menu. So the stepper max speed is selected. Then we put this symbol there, this larger symbol, and it will indicate the user that we selected this menu. Otherwise, it just deletes that part by overwriting the larger symbol with a set of spaces. So this is again very simple, and it's always the same. The only thing that changes is the name of the variable here. And then let's see what happens with the up button. Again, we just read the button, and this is sort of fixed if you are using my PCB. So this is good. And then we can only press the button with this kind of time separation, 300 milliseconds. So you cannot press it quicker. It will not detect, the code will not detect more clicks if you click it faster than this. So this is basically used if you are in one of these menus where you change a value. It's just used to have larger increments that you can do with the rotor encoder. So basically, if you are in the stepper max speed menu, then you add 40 to the stepper max speed instead of 1. So this is just a larger jump. And the same principle for everything. Acceleration, again, you add 40. Number of turns, you add 10. So it depends on the order of magnitude of a certain variable. So for example, the wire diameter, we know that we are in the millimeters range. So here we just use 1/10 of a millimeter and so on. And then we can check if the winding is selected. So if the winding is selected and the winding is not running, then we can start the winding. And what we do basically is that we zero the positions. So we set the origin at the current position of the main shaft and the feeder shaft. We recalculate the speeds. And I have a video on this, so please refer to that video about how the mathematics looks like behind the calculation of speeds, distances, lengths, and so on. So we calculate the speeds, and then basically we just set up certain values for the distance to be moved by the stepper motors, and then we update their speeds, and we say that the winding is running. And then finally we have two options which are identical basically, but what we do here is that we can move the stepper motors with the buttons, and this is how I do it. So I just update the let's say target distance expressed in steps. So the current position plus 160, which is 1/10 of 1600, so 1/10 of a turn, or 36 degrees if you like to see it in degrees. So we update the target position, we just write more or less reasonable speed, and we say that okay, we set the target position with this variable which we just calculated. And the same happens with the feeder as well. So it's basically the same, but the feeder is more sensitive to the movements, so we have just 32 steps here. And then just the typical value changed, so we update the display, and we block the button presses for 300 milliseconds. And I'm not going to explain this, because this is the down button, is the same but in the other direction. So you decrease the values or you move in the negative direction. So I can close this guy here, and I can close this guy here. So here I explain everything here, but again I have a video on a bit more deeper details of the mathematics, so please check that video if you are very interested. So I calculate the turns per layer. So I know that, for example, we have a certain bobbin width and we have a certain wire diameter. So based on this ratio, I can calculate how much turns I can fit in one layer. So to go from the left side of the bobbin to the right side of the bobbin, for example. And then if the auto winding is enabled, then we calculate the main shaft total steps based on this. So this is basically number of turns So the total number of turns, let's say 200, times the main microstepping, which is usually 1600. And then this will give us the number of steps for the main shaft to basically make those 200 turns. And here's an example with 160 turns. But if and then here the main shaft will go without any stop until it does, let's say this example, 160 steps. And then if the auto winding is not enabled, which means that the feeder and the main shaft stepper will stop at the end of each layer, then the main shaft total steps is just the turns per layer times the main microstepping. So it means that if you can fit only 30 turns on a layer, so you go from left to right or right to left, then you multiply that 30 turns with the 1600 steps per turn, and this basically stops the stepper motor of the main shaft after completing these steps. So this is done. Here we have number of layers, which consists of the ratio of number of turns divided by turns per layer. So for example, here I wrote that if we have 160 turns and if we have 40 turns per layer, then we have 4 layers. But as you can see, I'm using the ceiling here because we have to round this up. Because of course, if we have, for example, 50 turns and one layer can accommodate 40 turns, basically we have 2 layers. But if you just do the math and calculate this number, that is just 1.25. So that's not 2 layers. But if we look at the bobbin like physically, then we see that that is 2 layers. So we have to wind it up because we have to round it up because this will be used in later calculations, and it will be important to have this at the correct value. Then I have another value which is called layers to do, and that is basically just number of layers, but I need this layers to do because this will be used as a dynamic value. And then here is another tricky calculation that if the number of layers is larger than 1, then the feeder shaft's total steps, so the stepper motor which moves the feeder, is the bobbin width times the feeder microstepping, so 1600 divided by 5. So this is 320. So yeah, basically just this is the total steps for the feeder. So it covers the whole bobbin width, because we know that we have a full layer when we use this formula, a full layer to finish. But if we have like a fraction of a layer, like in this example I showed that we have 1.25 layers, that 0.25 layer and the equivalent steps is calculated here. So we take the wire diameter and then we basically calculate how many turns we have to do within that fraction layer by this formula, and then we get the number. So then that's very simple. And finally we calculate the speed of the feeder, and yeah, I just have the example here. So this is how it works. So this formula makes sure that the feeder is synchronized with the main shaft. And the direction multiplier is obviously 1. So first we start in the positive direction, and the total wire length is 0. So we reset the number here. So this was the calculation for the speeds and for the turns and steps. So now we look at these check steps, which runs in the main loop. So this checks the feeder. So if the winding is running and the feeder finished a layer and we have more layers to do, then we check something more. So a lot of, let's say, embedded ifs or nested ifs. So if the auto winding is enabled, then we just go to the winding function. But If the auto winding is not enabled, and this is when we ask the user to press a button, what we have to do is that usually I notice that there is a very small discrepancy between the finishing times of the main shaft and the feeder, and that is because the main shaft is a few 10 or sometimes few hundred steps behind the feeder, so the feeder finishes earlier in a layer than the main stepper motor. So in this while we finish the steps on the main shaft, and this will not cause any troubles with the wire, so don't worry, because usually it's just half turn or one turn, so it's not a big deal. And once that is finished, then we get the code stuck here and tell the user to press up to continue. So as long as this is 1, so as long as we don't press the button, we don't do anything with the code, we get stuck here and we just print this message. So we run this function which does some extra calculations, and then we have to see what happens now. So we check how many layers are left. So if the layers to do is 0, then we know that we are finished. So we just update the corresponding parts, and after that we return. So we jump out from here. If the layers to do is 1, so we are doing the last layer, then we have to calculate the steps left, because we can have an incomplete layer, as I said it earlier, that we have 0.25 layers left. So we calculate the equivalent steps for a fraction of layer, and then we update the speed for the main shaft. Otherwise, so there are multiple layers left, we just continue with this, which is usually a full layer of steps, and then we update the speed, we update the display again, and that's all. And finally, we have this part that if the main stepper distance to go is 0 and there are no more layers to do, then the winding is running is false, so we don't let the functions enter into any winding related stuff anymore. Then we calculate the total wire lengths based on this formula, which I explained in my video, so check it. And then I do a bit of a cheating here, so the number of turns done will be equivalent with the number of turns that we asked from the wire, from the coil winder to do. And then we update the display, and that's all. So here we did this winding function, and also here, so let's see what that does. So the winding function, it calculates the total wire length. Again, one of my previous videos showed this, how it's done, showed the mathematics and some geometry, and then we calculated the wire length. When we enter this function, we have to decrease the layers to do by 1, and then we have to flip the direction of the feeder, so we multiply it by -1. So if it was 1, it becomes -1, if it was -1, it becomes 1. And then based on this decreasing of the value, we check how many layers are done or how many layers have to be done. So if the layers to do is larger than 1, so we have multiple layers to do, then we tell the feeder to move this amount of steps. So then it will move this amount of steps, and we update the speed. If we are doing the last layer, so the layers to do is 1, then we do this amount of steps, which is different from the amount of steps for a full layer. Because if there are multiple layers to do, so if we are in this if branch, you can see that we use the feeder shaft total steps variable. But down here, I'm not using that because I calculate the exact number of steps needed to finish, let's say, just 1/3 of the layer. So that is done here, and that is illustrated with an example here. And then after giving the move command, I also set up the speed. And else, so else means that the layers to do is 0, we are finished, so we don't do anything else more. And you can see that here is a comment with serial.println, which was used for myself to do some debugging. And if I close this, and of course I close this, we can see that we are finished. So I explained everything, and I think this should be fine. So the code works, the PCB works, and everything seems to be fine. So I upload this code to my website. So once again, visit my website, link in the description, and there will be this code, which you can use as you want. And once again, don't forget to visit the website of the sponsor of this video, PCBWay. So go to PCBWay.com, and also check the link in my website, which will lead you to the PCB. So you can buy the PCB directly, and it will make your life hopefully easier, because you don't have to struggle with the circuit. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.